Across thousands of years, 3 colossal stones, each heavier than a fully loaded Boeing 747, were somehow raised nearly 20 feet above the ground, forming the foundation of Baalbek's Temple of Jupiter. The textbooks credit Roman engineers, claiming wooden cranes and brute force did the job, but the math exposes something impossible. No Roman crane came close, and the telltale Lewis holes that mark their handiwork are missing entirely. If modern cranes would buckle under the load, what exactly are we looking at, and why has mainstream history ignored these contradictions? The stakes are simple. Understanding how the Trilithon platform was really built means rewriting the origins of Western civilization as we know it. The real answer starts now. The numbers do not lie. The Roman Polypastos crane, the pride of ancient engineering, had a maximum lifting capacity of 60 tons under ideal conditions, with flawless ropes, strong timber, and a full team of men at the capstan. That is not an estimate, it is the upper limit confirmed by ancient texts and modern reconstructions. The Trilithon blocks at Baalbek weigh roughly 800 tons each. 800 divided by 60 equals 13 1/3. Even rounding up, that means at least 14 full-sized cranes would be needed to lift a single block, assuming each crane could carry its theoretical maximum and the load was perfectly balanced across all points. Each polyspastos was a massive piece of equipment, with a mast reaching 10 to 15 meters high and guy ropes that had to be anchored 10 to 20 meters out from the base for stability. In practice, every crane would occupy a working circle up to 30 meters across. 14 cranes operating side by side would require a continuous stretch of stable ground, each with its own anchor points and no interference between neighbors. The western face of the Baalbek podium, where the Trilithon sits, is about 60 meters long. Even spacing the cranes evenly along that wall would cram them together with only a few meters between mast feet. Their guy ropes would cross and tangle. Many anchors would have to be set beyond the terrace edge on sloping or unstable ground. The platform itself is not a broad level field. The podium rises almost directly from the edge of a natural limestone terrace. There is only a narrow strip of workable ground before the terrain drops away toward the valley. There is no evidence of an engineered staging yard or a sprawling crane platform. Nothing suggests that the Romans prepared the ground for such an operation. Even the most generous engineering assumptions run into the same hard limit. There simply is not enough room for 14 heavy lift cranes, each demanding a 20-meter working radius to operate side by side in front of the Trilithon. This is not a matter of missing blueprints or lost technique. It is a question of simple physics and geometry. The load is too great. The space is too tight. The ground offers nowhere near the footprint required. Any claim that Roman cranes alone could have lifted the Trilithon stones must first answer the arithmetic. The numbers make it clear. The official story does not add up. Subscribe for more forensic breakdowns like this. The real story is always in the math. A single glance at the site plan exposes the real problem. The western face of Baalbek's podium, where the Trilithon blocks sit, stretches about 60 meters from end to end. That is the full length available for any lifting operation. Now imagine trying to line up 14 massive cranes along that edge. Each one would be a towering structure, with a mast reaching 10 to 15 meters high, and guy ropes that need anchoring at least 10 to 20 meters out for stability. Even the most conservative engineering models demand a working circle of 20 to 30 meters in diameter for each crane. Multiply that by 14, and the required space balloons far beyond what the site can offer. The ground in front of the Trilithon is not a flat field or a bustling Roman construction yard. It is a narrow terrace, hemmed in by the natural drop of the limestone bedrock. There is only a slim strip of relatively level ground before the terrain plunges toward the valley. Site surveys and modern three-dimensional scans confirm this constraint. The workable area is measured in single-digit meters, not the broad expanse a multi-crane operation would demand. There is no trace of a massive artificial platform, no evidence of a staging yard built out to support the immense weight and spread of so many cranes. Cranes of this scale cannot simply be squeezed together. Their guy ropes would have to cross and anchor into ground that does not exist. Much of the rope would hang over a steep drop with no solid base for the anchors. Even if you tried to compress the spacing, the masts would crowd each other, the ropes would tangle, and the risk of catastrophic collapse would skyrocket. The geometry is unforgiving. 14 cranes, each needing a safe working footprint, simply cannot fit along a 60-meter wall with only a few meters of stable ground in front. The physical reality on the ground turns the arithmetic shortfall into a spatial impossibility. No archaeological trace supports the existence of a sprawling crane yard here. There are no post holes, no anchor points, no remnants of timber platforms or earthworks that could have supported such a dense array of giant machines. The site is what it has always been, a narrow shelf at the edge of the valley with the Trilithon blocks perched 6 meters above the ground, resting on another course of multi-hundred-ton stones. The logistics of staging even a handful of heavy-lift cranes on this terrain are daunting. Staging 14 is out of the question. This is not a matter of missing blueprints or lost Roman ingenuity. It is a matter of hard limits, of physics, of geometry, of the landscape itself. The official story requires a fantasy construction site that simply is not there. If you appreciate this kind of forensic breakdown, subscribe for more investigations that put the real numbers and the real ground under the microscope. Roman engineering left a distinct signature wherever it operated, and nowhere is that more evident than in the way heavy stones were lifted and set into place. The standard method relied on a specialized tool, the Lewis iron. This device worked by inserting dovetail-shaped iron keys into a precisely carved socket on the top of a stone block. When tensioned by a crane or pulley, the Lewis iron would grip the stone from within, allowing it to be hoisted vertically with control and safety. These sockets are not random holes, they are geometric, often trapezoidal, cut specifically to match the iron profile. The system was so reliable that it became a hallmark of Roman construction from Britain to Egypt. At Baalbek, the upper layers of the temple, the columns, the architraves, and the decorative blocks display this method clearly. Many of these stones, weighing from a few tons up to several dozen tons, show the telltale cut socket geometry on their upper faces. Even after centuries, these indentations remain visible, sometimes patched or filled after the block was set, but always unmistakable to anyone familiar with Roman techniques. The presence of these sockets is not just a technical detail, it is a kind of fingerprint proving that Roman cranes and Lewis irons were at work. This pattern repeats throughout Roman sites. Whether in the Pantheon portico or the arches of the Pont du Gard, the Lewis hole is as Roman as the Corinthian capital. It is a baseline expectation. Where Romans lifted, the socket remains. The logic is simple: no socket, no lift. The next question then is whether this same signature appears on the largest stones at Baalbek's base. Subscribe for more forensic engineering that puts ancient methods under the microscope. Inspection of the Trilithon stones reveals a striking anomaly. On almost every Roman construction site, Lewis holes are a given. These are the sockets carved into the tops of blocks, designed to grip the stone securely for lifting. At Baalbek, the upper courses of the temple podium and the columns show this signature clearly. The Lewis holes are there, cut with geometric precision, matching the iron keys and lifting gear the Romans depended on. Yet when attention turns to the Trilithon, those 3 blocks, each weighing 800 tons, there is nothing. No sockets, no dovetails, no evidence on any exposed face of the standard Roman attachment points. Surface inspection reports and high-resolution photographs confirm the absence. The upper faces of the Trilithon are smooth and unbroken, aside from the scars of weather and time. The ends and sides, visible from the retaining wall exterior, show only the tight seams where block meets block. The geometry is so precise that a knife blade cannot slip between them, but there is not a single lifting hole or clamp recess to be found. This is not a minor oversight. Roman engineers did not hide their methods. They left behind a clear, repeatable pattern. Where their cranes worked, the evidence remains carved in stone. The lack of Lewis holes on the Trilithon is not just unusual, it is a direct contradiction of the Roman method. For blocks of this scale, the omission cannot be explained away by erosion or later repairs. If the Romans had lifted and set these stones using their own technology, the Lewis holes would be there. Their absence is a silent but decisive argument. The Trilithon was not handled by Roman cranes. Subscribe for more forensic breakdowns that challenge the textbook version of history. In the limestone quarry southwest of Baalbek, the scale of ambition becomes almost incomprehensible. Here lies the stone of the pregnant woman, a single block of limestone more than 20 meters long and weighing close to 1,000 tons. For centuries, this unfinished monolith has stood as the largest known quarried stone in the world. Then, in 2014, a team from the German Archaeological Institute, led by Jeanine, Abdul, Massih, excavated beneath the famous block and revealed a second monolith still connected to the bedrock. Its dimensions are staggering, nearly 20 meters long, 6 meters wide, and 5.5 meters tall. The estimated weight is 1,650 tons. No other stone ever cut by human hands comes close. This discovery rewrites the limits of what ancient builders at Baalbek set out to achieve. The Trilithon blocks at the temple podium, each weighing around 800 tons, already defy the known engineering of the Roman world. Yet the quarry proves the builders were not just capable of carving stones twice that size, they were actively preparing to move them. The unfinished state of the 1,650-ton monolith tells its own story. It was shaped, measured, and separated on almost all sides, left attached only at the base, as if waiting for a final decision or a change of plan. The intention was clear. This stone was meant to be transported, not left as a monument to failed ambition. The quarry itself sits roughly 900 meters from the temple site, on slightly higher ground. The terrain is uneven, the distance considerable, and the logistics daunting. But the existence of such a colossal block prepared for movement forces a reckoning with the scale of the project. This was not an isolated feat or a one-off experiment. The quarry output, an 800-ton Trilithon, a 1,000-ton pregnant woman, and now a 1,650-ton monolith, demands a level of organization and planning that challenges every textbook assumption about ancient construction. The numbers do not just impress, they overwhelm. The largest cranes in the Roman world, the polyspastos, were never designed for anything approaching this weight. No documented ancient machine and no known combination of manpower could tackle a load of 1,650 tons. The quarry blocks of Baalbek are not just bigger than anything the Romans ever moved, they are bigger than almost anything moved in the pre-industrial world. If this scale of ambition resonates with you, subscribe for more forensic engineering that puts ancient achievements under the microscope. The quarry sits about 900 meters from the temple podium, separated by a landscape that is anything but unforgiving. The path between them is not a straight paved Roman road. It is a stretch of uneven ground with pockets of soil, shallow depressions, and patches of exposed limestone. Elevation data shows only a modest difference in height, 10 to 20 meters over nearly a kilometer, so the grade averages just 1 or 2%. That may sound gentle, but for an 800-ton block, even a slight slope turns the physics against you. On a downhill segment, the stone would accelerate uncontrollably. On an uphill segment, the force required to keep it moving multiplies. The favored academic model relies on timber rollers, thick logs, likely cedar or pine, lined up beneath the stone. In theory, these rollers, greased and pushed or pulled by capstans, would let the block glide forward. But the numbers tell a different story. Lebanon cedar, the best available wood, can handle about 4 to 8 megapascals of pressure across the grain before it starts to crush. With an 800-ton block spread across 10 rollers, each roller is subjected to pressures well above that threshold, often in the double digits. The wood does not explode, but it flattens and deforms, increasing the contact area until the pressure drops, but not before gouging deep trenches into any soft ground beneath. Soil is the next weak link. On bare earth, the pressure under each roller is enough to turn the surface to mud. Even compacted clay or gravel cannot withstand the repeated blows of a stone this heavy rolling over it. The result is immediate rutting. Rollers sink, friction skyrockets, and the entire operation grinds to a halt. Only a continuous rock-hard causeway cut into limestone bedrock or armored with heavy stone or timber mats could survive the assault. Over 900 meters, building such a track would rival the effort of carving the monolith itself. Yet no archaeological survey has found evidence of a continuous engineered haul road linking the quarry to the podium. There are fragments of ramps and hints of prepared surfaces near the site, but nothing that matches the scale or durability required. The physics are simple. Without a specially built road, the roller method fails before it even begins. The terrain at Baalbek is not a blank slate. It is a complex, uneven, and unforgiving surface. The absence of a surviving causeway raises a fundamental problem for the standard explanation. The ground would have swallowed the rollers whole long before the block reached the temple platform. For more forensic breakdowns like this, subscribe and keep the hard questions coming. Standing before the western face of Baalbek's podium, the first thing that draws the eye is not the size of the stones, but their surface. The Trilithon blocks, looming 6 meters above the valley floor, are scarred with deep vertical channels. These are not random nicks or accidental scrapes. They run in straight parallel lines, fluting that cuts down the face of the limestone, sometimes half a meter deep, sometimes so narrow that only a fingertip can trace the path. The lower courses, including the Trilithon and the blocks beneath, are marked by this pattern from end to end. Each groove carves a shadow, accentuating the mass of the stone and the passage of time. In contrast, the Roman masonry above tells a different story. The columns and entablatures carved in the ornate Corinthian style show only gentle rounding at the corners and a softening of detail. The capitals retain their acanthus leaves, the fluting on the shafts is crisp, and the decorative moldings are still legible despite 2,000 years of exposure. The weathering here is shallow, surface pitting, minor cracks, the slow abrasion of wind and rain. Nothing like the pronounced vertical erosion that defines the base. Photographic surveys and on-site measurements confirm the disparity. Where the upper stones show millimeters of surface loss, the lower megaliths have lost centimeters, even decimeters in places. The contrast is unmistakable under direct sunlight. Bright, clean Roman stonework perched atop a foundation that looks ancient, battered, and almost geological in its erosion. The vertical channels on the Trilithon blocks are especially striking after a rain, when water traces the same paths down the face, reinforcing the grooves cut by centuries of runoff. No mortar fills the joints between these stones. The fit is so precise that the seams are barely visible, even as the surfaces around them are worn and fluted. The Trilithon's weathering is not just a mark of age, it is a visual record, a surface archive, hinting at exposure far longer than the stones above. This layered effect, the crisp Roman temple resting on deeply eroded megaliths, demands explanation. The evidence is right there in the stone, two histories, one on top of the other. The contrast between the battered megaliths at the base and the relatively fresh Roman stonework above is not just an aesthetic detail. It is a physical record of time. Deep vertical channels scar the lower blocks, while the upper courses, carved in the ornate Corinthian style, retain sharp lines and crisp ornamentation. Photogrammetric surveys and on-site measurements show the lower stones have lost centimeters, sometimes even decimeters, to erosion. In comparison, the Roman blocks above have weathered only a few millimeters. Their details softened, but not erased. This pattern follows the logic of water. Rainfall runs down the face of the wall, tracing the same grooves year after year. On the exposed megaliths, runoff carves deep channels, especially where joints or surface irregularities guide the flow. The Roman masonry above, set back and shielded by cornices and projecting moldings, is less vulnerable to this kind of attack. But the scale of the difference goes beyond what can be explained by microclimate or runoff alone. For vertical fluting this pronounced to develop, the lower stones must have stood exposed for a far longer period, centuries, if not millennia, before the Roman temple ever crowned the platform. Mainstream archaeologists often attribute the weathering gap to differences in stone quality or local water flow. Yet geological surveys show both layers are carved from the same Cretaceous limestone, quarried within 1 kilometer of the site. The only major variable left is time. If the base had been set at the same moment as the Roman superstructure, both should show similar degrees of erosion. Instead, the foundation looks ancient, almost geological in its wear, while the temple above still carries the marks of the chisel. The evidence is written in the stone. 2 histories separated by an invisible gulf of years. The lower megaliths bear the scars of an ancient age long before the Roman Empire, hinting at a forgotten chapter in Baalbek's story, one where the foundation predates the temple by far more than a single generation. Standing at the base of Baalbek's western podium, the mind grapples not just with the mass of the Trilithon blocks, but with their astonishing precision. Each limestone giant, nearly 20 meters long, 4 meters tall, and over 3 meters thick, rests perfectly on a bedding course of smaller but still massive stones. The Trilithon is not on the ground. It sits 6 meters or nearly 20 feet above the valley floor, supported by a substructure that itself weighs hundreds of tons. This is not a pile of boulders. It is a deliberate, multi-layered platform engineered for stability and scale. What sets the Trilithon apart is the way these blocks are joined. Along their seams, the gap is so fine that a needle cannot slip between the stones. No mortar, no filler, just limestone against limestone, locked so tightly that the joints are almost invisible even after millennia of weathering. Surveyors have measured tolerances down to fractions of a millimeter over lengths of nearly 20 meters. The stones are not just close, they are aligned in 3 dimensions, with no measurable tilt or step between them. The platform's face runs straight and true, as if cut by a machine, not by hand. This level of precision demands an explanation. The bedding layer beneath the Trilithon adds another layer of complexity. These supporting stones, each weighing 300 to 400 tons, were first set in place to create a level foundation. Only then could the Trilithon be placed on top, lifted or slid into position with such accuracy that the contact surface is almost seamless. It is a feat that demands not only immense force, but a mastery of geometry and load distribution. The entire structure rises from the edge of the limestone terrace, with the Trilithon forming a continuous elevated belt, an architectural cross-section that reveals a hierarchy of stone from the smaller supporting blocks to the 3 colossal slabs above. This combination, 800-ton stones, needle-tight joints, and a 6-meter elevation defies the logic of ancient construction as we understand it. The engineering paradox is not just about weight, it is about precision at scale, achieved at a height that complicates every step of the process. Any credible explanation must account for not only how these stones were moved, but how they were fitted and set with such exactitude on top of an already massive bedding course high above the ground. The Trilithon's perfection is not an accident, it is the product of a method we have yet to fully comprehend. If Roman cranes and rollers fall short, what about the old-fashioned lever? Ancient engineering texts describe lever systems used to move obelisks and massive columns, timber beams, fulcrums, and counterweights multiplying human force. On paper, the lever is the simplest machine known to civilization. In practice, scaling it up for an 800-ton block is another matter entirely. To make a lever system work at Baalbek, the builders would need beams long enough and strong enough to survive the forces involved. Even the densest old-growth cedar or oak can only take so much before it splinters. For a block nearly 20 meters long and 4 meters high, a lever arm would have to be both immense and perfectly placed. The fulcrum, usually a stone or another beam, would need to be set in a socket or pit anchored deep into bedrock to avoid shifting under load. As the block is jacked up, cribbing, stacks of smaller stones or timbers would be inserted underneath, raising the block in increments. Over many cycles, the stone could be lifted to podium height. In theory, a crew could repeat this process inch by inch until the block reached the required elevation. This method is not just a thought experiment. Modern heavy riggers use similar techniques for moving transformers and bridge spans, albeit at a much smaller scale. The real question is not whether it is possible in principle, but whether there is any trace of such an operation at Baalbek. Archaeologically, lever systems leave a distinct footprint: anchor sockets carved into bedrock, post holes for timber supports, counterweight pits, and wear marks where beams pivoted under load. At Baalbek, no such features have been documented in published surveys around the Trilithon. The podium's edge is clean, the terrace shows no obvious anchor pits, and the ground in front of the wall bears no sign of massive lever operations. It is possible that later construction, soil movement, or simple erosion erase these traces. Timber, unlike stone, leaves little behind after centuries. But at other ancient sites, for example in Egypt, lever sockets and anchor points are often preserved even after thousands of years. Their absence at Baalbek does not prove the method was never used, but it does mean the evidence is ambiguous. For the practical skeptic, the lever remains a testable hypothesis, simple, scalable, and grounded in physics. But without the physical signatures, anchor pits, fulcrum scars, or counterweight foundations, the lever solution is still waiting for its smoking gun. Speculation fills the void where hard evidence runs thin. When the math rules out cranes and the terrain defeats rollers, the search for answers turns to the margins of engineering and materials science. One alternative, championed by Joseph Davidovits, suggests that the megaliths of Baalbek were not quarried and moved at all, but cast in place using a kind of ancient geopolymer concrete. The theory proposes that limestone, crushed and mixed with an alkali binder, was poured into wooden molds and left to set, creating blocks that only mimic natural stone. If true, this would upend every assumption about ancient construction. But so far, thin section petrography and chemical analysis of Baalbek stones show the microstructure and fossil content of natural Cretaceous limestone, not an artificial mix. No trace of chemical binders or casting layers has been found. Without this evidence, the geopolymer hypothesis remains unproven, a technical possibility, but not a demonstrated fact at Baalbek. Other ideas drift even further from conventional engineering. Some propose that the builders harnessed resonance or sound, acoustic levitation, to move the stones, citing legends of lost knowledge and the silence of the archaeological record. No ancient texts describe such a process, and no experiment has ever demonstrated the lifting of multi-ton blocks by sound alone. These concepts remain thought experiments, untestable at present and unsupported by physical traces at the site. Acoustic theories are intriguing, but they require extraordinary evidence. The lever and crib method remains the most plausible mechanical solution, but as already shown, the absence of anchor pits or fulcrum scars at Baalbek keeps it in the realm of hypothesis. The lack of direct evidence is not proof of absence, but it does leave the door open for further research. What can be done now is clear. A systematic program of high-resolution petrographic analysis, ground-penetrating radar along the quarry to podium route, and targeted excavation at the podium margins could reveal hidden roadbeds, compacted layers, or anchor points, signatures of lost infrastructure or techniques. Laboratory experiments to test compressive strength and microstructure of the Trilithon blocks, searching for signs of casting or unusual composition. Digital simulations using finite element modeling to stress test every proposed method, from multi-capstan jacking to hypothetical acoustic lifting under realistic conditions. Field surveys and targeted trenches along the quarry route and podium margins to look for engineered causeways or anchoring features. The evidence checklist is simple: chemical binders in the stone, radar traces of engineered causeways, tool marks or sockets in the podium, and experimental replication at a meaningful scale. Each testable claim invites the technical community to weigh in, not with speculation, but with data. The mystery of Baalbek will not be solved by stories alone. It demands measurements, experiments, and the courage to follow the results wherever they lead. If you have access to lab equipment, ground-penetrating radar, or digital modeling tools, the next breakthrough may come from outside the academy. Post your findings, challenge the assumptions, and help turn this ancient puzzle into a modern engineering case study. The future of this question belongs to evidence. Today, Baalbek's Trilithon stands as a physical equation history cannot solve. They are three 800-ton stones that outstrip the limits of ancient and modern lifting technology. As new discoveries upend what we thought we knew, the site reminds us that not all human achievements fit our narratives. The real mystery is not who built it, but how much knowledge we have truly lost. Sometimes the foundation beneath us is older than the stories we build on top. Share your thoughts below.